These lecture slides constitute part 3 of set 1. In this presentation, you will learn about Boolean algebra and its application to digital circuit design or synthesis. Reference for further reading is shown here. The next few slides are about a special kind of algebra called Boolean algebra. It is a bit abstract and dry, but the material is fundamental to logic design. Boolean algebra was introduced by George Boole in 1854, and then in 1930s it was shown by Claude Shannon that the algebra can be very useful to describe logic circuits. Axioms/postulates and theorems of Boolean algebra are very useful to simplify logic expressions and to prove equivalence of expressions. So here is the definition of Boolean algebra. It is defined by a set of elements denoted as B together with two binary operations, addition and multiplication, that satisfy the following set of postulates given in the next slide. In this slide, while showing the postulates of Boolean algebra, I'll be giving some examples. In my examples, I'll assume that x, y, z are in B. Postulate number 1. This says that the algebra is closed with respect to addition and multiplication. That means if you take any two elements from B and you add them, the result would be also in B. Similarly, if you multiply x and y, then the result of the multiplication will be also in B. Postulate 2 is about the existence of identity elements. There exists an identity element with respect to addition, and that element is denoted by 0. Also, there exists an identity element with respect to multiplication, and that is denoted by 1. So if x is added to 0, which is the additive identity, then the result is x. Similarly, when we multiply x to multiplicative identity 1, then the result is x. Postulate 3 is about the commutative property of the algebra. So if you take two elements, x and y, and you add them, the result is equal to adding y to x. Similarly, the result of multiplying x to y is equal to the result of multiplying y to x. Postulate 4 is about the distributive law of the algebra over addition and multiplication. On the left-hand side of this expression, we have x multiplied to the sum of y and z, and the result is equal to the product of x and y, and it's added to the product of x and z. The dual property is shown here. In this case, the sum is distributive over the product here. So x plus y times z is equal to x plus y times the sum of x plus z. Postulate number 5. For each element a and b, there exists an element a prime, that's part of b, such that a plus a prime is equal to 1 and a times a prime is equal to 0. Note that this 1 is the identity, multiplicative identity we mentioned in postulate number 2. Similarly, 0 is the additive identity that we have in postulate 2. The last postulate is number 6. There exist at least two elements a and b in set B such that a is not equal to B. If we assume that set B has two elements, 0 and 1, and addition and multiplication are actually logical OR and AND operations, then it is easy to see that all 6 postulates given in the previous slide hold, where A prime is the complement of A. In the rest of this course, we will use this Boolean algebra. Now I show you some useful properties and theorems of Boolean algebra. In this slide, I am assuming that x, y, z belong to set capital B. Property number 1, which is very obvious, x times 0 is 0, x plus 1 is 1. Property 2 is actually postulate number 2. Property 3 is x times x is equal to x, and x plus x is equal to x. Property 4 is x times x prime is equal to 0. On the other hand, x plus x prime is equal to 1. This is actually from postulate number 5. Then property 5 is if you take complement twice, then you get the original x back. Property number 6 is the commutative property of the algebra. That means is really postulate number 3. Property number 7 is associative law, which says that if you take x and then multiply this to the product of yz, you can actually change the precedent. That means you first multiply x and y, and then the product is multiplied to z. Same thing goes for the addition operation. Property number 8 is actually postulate number 4. Property number 9 is very actually important. We'll be using this one later in simplifying logic circuits, and this is known as De Morgan's law. It says that if you take product x and y and take complement, then that is equal to taking complement on each x and y and then adding them. The dual properties here, if you take sum of x and y and take complement, that is equal to taking complement of each x and y and then making a product of them. Theorem number 10, this is about absorption, and this is shown here. You can see some duality in relationships by interchanging multiplication and addition with 0 and 0 with 1. You can try to prove some of these theorems from postulates or some other proven theorems. Synthesis. Synthesis is the implementation of a circuit. We can draw circuits using gates to show the realization of functions. We have already seen the synthesis of a simple circuit for a function represented in algebraic form. This was part of a previous set of slides. Using techniques like Boolean algebra, a function can be manipulated, leading to multiple designs for the same function. The cost of different designs can be different. We will measure the cost in terms of area of the circuit. For this, we will consider the number of gates plus the number of inputs to the gates. We will also assume that true as well as complements inputs are available free of cost, meaning that if x is available, then so is x prime. Suppose we are given the following truth table, and we want to synthesize a circuit for function f. The truth table shows there are two variables x1 and x2, and the function is denoted as f, and function is 1 here, here, and here. Here's one possible procedure for designing the circuit. First, we create a product term that has a value of 1 for which f is equal to 1. F is equal to 1 is here, here, and here. And then we take logical sum, meaning logical OR of all these product terms. The resulting function is shown below. So this 1 corresponds to this product term. This 1 corresponds to this product term. Finally, this 1 corresponds to this product term. And here we have a circuit diagram for the term that, or the expression that we have derived in the previous slide. These are the two inputs, and these NOT gates are used to get complements of x1 and x2, and the product terms in the previous expression are generated through these three two-input AND gates. Finally, the output of these AND gates go to a three-input OR gate, and the output is the function f. This is called sum of products because here we are summing three products in this case. A little bit simpler circuit is possible. So we write the previous function as follows. This is the expression that we derived previously. Now we use distributive law that we have seen earlier. So we can combine these two terms as follows. So we are taking x1 prime out, and then using one of the properties we discussed earlier, we have this expression. This expression is simpler than this because this expression requires 1, 2, 3 two-input AND gates and one three-input OR gate, and then we also need two NOT gates. One NOT gate is for this, another NOT gate is for this. On the other hand, this expression requires one two-input AND gate and another two-input OR gate. Of course, we also need one inverter for inverting x1. After this could be further simplified. After duplicating a term and then using distributive law, we can write this expression as follows. Why we are doing this? If you look at the middle term, this middle term can be combined either here or here. So by having a duplicate of this term, now we are combining this term as well as this term, okay, with this common or two same terms. So these two terms result into this part of the expression, and these two terms result into this part of the expression. And after doing some simplification, we have x1 prime plus x2. This is much simpler than what we had earlier, and of course much simpler than this one. And this is a circuit diagram realizing this simplest expression. x1 and x2 are the input. x1 is inverted through this NOT gate, and then we use this two-input OR gate to sum them up to get F.